are these inductors, some inductor questions. These are not RL circuits, these are just inductors. So this is where we would use the formulas that have to do with the current and voltage across an inductor. So that would be these formulas right here. Might as well copy them. Alright, so we have activation of a switch at t equals 0 in a certain circuit cause the voltage across a 20 millihenry inductor. So our inductance is 20 times 10 to the negative third. To exhibit the voltage response, we have this voltage response. Notice that the voltage here is given in millivolts. So V of t really equals 4 times 10 to the negative third e to the minus 0.2 t volts. For t greater than or equal to 0, determine I of t for t greater than or equal to 0, given that the energy stored in the inductor at t equals infinity is 0.64 millijoules. So at t equals infinity, the energy, I don't like using W, but they use W. W is 0.64 times 10 to the negative third joules. So that's at infinity. So what we can do with this is we can find, we could start, there's two different things we could do first. We could either find what the current is at infinity using this information, or we could find this integral. And I'm going to find the current at infinity first, just because that's the order that I did it. So at infinity, the energy is 0.64 times 10 to the negative third, and that equals 20 times 10 to the negative third times I squared, and that ends up with I equaling 0.253 amps. If you solve for I, that's an I. And this is at infinity. Now, we need to find I of t, and in our formula, it doesn't say I at infinity, it says I at t0. Well, t0 is 0, so we'll have to come back to that when we get there. So I of t equals I at 0 plus 1 over L times the integral from 0 to t of v dt. So I of t equals I of 0 plus 1 over, and L was 20 times 10 to the negative third. 20 times 10 to the negative third, integral from 0 to t, and V is 4 times 10 to the negative third, e to the minus 0.2 t dt. Or I of t equals I of 0 plus 1 over 20 times 10 to the negative third times 4 times 10 to the negative third. And then when we integrate, we'll get times 1 over negative 0.2 from our e. And then we get e to the negative 0.2 t from 0 to t. And that equals I of 0 plus, well, I think it's actually a minus. If you multiply all that together, I believe you get negative 1. Negative 1. Now be careful with e. When you plug in 0, you don't get 0. So first you plug in t, e to the minus 0.2 t minus, and then when you plug in 0, e to the 0 is 1, minus 1. So I of t equals I of 0 minus e to the minus 0.2 t plus 1. Okay, now is where I'm going to use what I found out about I at infinity. So I at infinity was 0.253, and that would be what I would get if I plug infinity into this right here. So I at infinity equals I at 0 minus e to the minus 0.2 times infinity plus 1. So 0.253 equals I of 0 minus e to the negative infinity is 0 plus 1. So I of 0 equals negative 0.747 amps. So now I can plug that in to here, and I get I of t equals negative 0.747 minus e to the minus 0.2 t plus 1. And then if I add the 1 to the negative 0.747, I of t equals 0.253 minus e to the minus 0.2 t. Yes.
You said how you found infinity again?
Yes. So I at infinity, okay, so they gave me that the energy at infinity was 0.64. And I know the energy at any time is 1/2 Li squared. And so particularly at infinity, if I plug in the energy that they gave me, which was 0.64 times 10 to the negative third, equals 1/2 times, I know the inductance is 20 times 10 to the negative third times I squared, I can solve for I. So this gets me I at infinity. Now what do I do with that? What I did with that is I waited until I got to this part where I solved for I of t, but it still had I of 0 in it. I had I of t equals I of 0 minus e to the minus 0.2 t plus 1. So this gets me the current. This is the current at any time t. So current at t. So I plug in t at infinity, or t equals infinity, because I know what the current is at infinity. I just found out. I found out that the current at infinity was 0.253. So if I plug in infinity for the time here, that should equal 0.253. And then e to the negative infinity is 0. And what this did for me is it allowed me to solve for I of 0, which was the whole reason, which is what I used it for. Other questions? All right.
Wait, can you go back up to where you solved for the energy again?
Right here.
So you said that the energy is 1/2.
Did I forget the 1/2? I forgot the 1/2 here.
Yeah.
Sorry.
Okay.
Yeah, that should be a 1/2. That this is the right answer, but that should be a 1/2.
Okay.
Yes. Okay, so now we are given the current, And we have to find the voltage, the power, and energy as functions of time. Okay, so voltage is L di dt. So voltage will be L, which is 0.5 times 10 to the negative third, times the derivative of this. So minus 4 just stays there. Derivative of 1 is 0. The derivative of negative e to the negative 0.4t is 0.4 e to the negative 0.4t. There's this unit step function at the end of it. That just means it's for time t greater than 0. That before 0 it's 0. And then if I multiply these together, I get negative 0.0008 e to the negative 0.4t volts. Which is the same as negative 0.8 e to the negative 0.4t millivolts. So that's the voltage. We're supposed to find the power. Power is I times V. So I is negative 4, 1 minus e to the minus 0.4t. That's I. V is 0.8 times 10 to the negative 3, that's my milli, times e to the negative 0.4t. So, if I multiply this out, was this supposed to be negative? This was supposed to be negative. I get 3.2 e to the negative 0.4t. That's this times negative 4 times 1. And then that's a negative, so negative, that's a negative. And then 3.2, and when you multiply, you add exponents, so e to the minus 0.8t. And I've got this times 10 to the negative third still in there, times 10 to the negative third watts.
And what is that outside of the parentheses? Is that the power of negative 1?
Nah, that's a negative sign.
Oh, okay.
It's supposed to go with that,
With the 8.
with the 8.
We're multiplying this by this.
Yeah, I multiplied the negative 4 and the negative 0.8 to get 3.2. And so I have 3.2 e to the negative 0.4t minus 3.2 e to the negative 0.8t milliwatts. And then we're also supposed to find the energy. So the energy is 1/2 Li squared. So that's 0.5, and L is 0.5 millihenries. And I is negative 4, 1 minus e to the minus 0.4t, and that's just amps, so I don't have any other 10 to the negative 3s to worry about, and this is squared. So if I take negative 4 squared, that's 16. 16 times 0.5 times 0.5 times 10 to the negative 3 gives me 0.004, and then 1 minus e to the minus 0.4 t squared, or 4 times 1 minus e to the minus 0.4 t squared millijoules. Okay, questions on that one?